So the power triangle, B in the top, that's power in watts. This is voltage, volts, and amperage, amps. So this is going to be called the power law. And this here is his best friend, EFF forever. It's Ohm's law. Resistance and amperage. If you see they have two values in common, they're just a little bit different how they are organized. So power is the rate at which the electrons do work. They push a motor, they produce heat. Unit is watts, and it's voltage times amperage, and it can be transferred to horsepower or watt or BTU hour. You can, this is, so we said that it's a rate, and we can transfer rates of power from one unit to another. It's the same thing. So you can see 1 horsepower is 646 watts, and 1 watt is 3.4 BTUs. Another common measure of watts is kilowatt, which is, what's 1 kilowatt?
What?
1 kilowatt.
Is 1,000 watts.
Yeah. It's 1,000. It's why do we do that? Because we don't want to deal with really big numbers. When they tell you your house is consuming 1 kilowatt an hour, that sounds much better than consuming 1,000 watts an hour. That's a lot. So just a rate. So 1 kilowatt is very, very common. Again, make sure you have consistency in units. If you get milliamps or megavolt, make sure you go to the basics. You want volts, you want amps, you want watts. You get kilowatts, transfer watt back into a kilowatt, back into watts. Okay, now the math issue. Very simple. If you want to find something in the bottom, you cover it. From top to bottom, you divide. So divide. If I want to find voltage, I'll divide power by amps. If I want to find amperage, I'll divide power by voltage. Good? If I want to find power, I'll multiply voltage times amperage. And the same thing here. Simple as that. I can write it down. So power equal voltage times amperage. Amperage equal power divided by voltage. Voltage equal power over amperage. They go here. Voltage equal amperage times resistance. Amperage equal R. R equal voltage over A. Okay, so keep that in mind. We'll do a few practice problems with that. Sometimes you need a combination. If, for example, you need to find the resistance or amperage, and you have only the power, so you're going to use a combination between the two triangles. I don't want to go through the square and the square root. No, we're going to just use one at a time and make things a little easier. Yes, you talk about that. Watt hour. Okay. So yeah, here's the book's notation. They use E for V, and they use circles. I like triangles. It's personal preference. Put diamonds if you want. I like triangles. So the same thing as you saw over there. This is how you find one of those components. So these are, I don't know about you, but this is a little bit confusing for me. So I don't use them. I guess use those two. It's basically telling you that you can use power using voltage and resistance without the amperage. So what they did, if you're interested to know how did this come about. So for here, if you want to find power with only the voltage and amperage, so power equal voltage square over resistance. Why? Assuming here we don't have the amperage, because power requires you to have voltage and amperage, and I will have the resistance in this triangle. So what they did is they went with resistance equal voltage over amperage, and they substituted that in here, and by doing so you get power equal V times V over R equal V squared over R. I don't know, I find it a little confusing.
I'm out.
So I will just go and find the resistance and the amperage and just substitute. Too much. Okay? So we'll do a few examples now and hopefully we'll get it. Let's do a review of the key terms we went through in this chapter. We're still in chapter 2, and we'll spend more time in chapter 3 as well to get just the basics out. Alternating current goes up and down. Ampere, unit of the current. Atom, smallest part of the element. Compound, more than one element. Conductor, conducting electricity. Current, flow of electrons. Direct current, DC, goes in one direction. Electric energy, form of energy, does work. Electric power, energy over time. Electric pressure, voltage. Electricity, same as current, flow of electrons. Electrodes, which you have in the battery. Two things that have different charges. Electrolyte, compound that is conductive, either paste or in liquid form or gel. Electrons, it's whatever spins around the atom. Element, field of force, that's where we had the coil, the magnet around it. Free electrons, electron at the outer orbit, that's easy to knock out. Insulator, somebody. What did you call it?
Wire.
Somebody doing all the talking.
We got it.
Lance, give me an example of an insulator.
It doesn't conduct. It's a
Example.
non-conductor. Wood.
Wood, rubber, good. Kilowatt hour. Sam,
Per hour.
1,000 watts per hour, unit for power. Law of electric charges. Got it.
Blank.
Opposite subtract.
Yeah?
And similar repels.
Remember that. Well, but matter. What's a molecule, Tim?
What's up on collection of elements?
Yes? More than one element, like water is a molecule, is not an element. Good. Neutrons, what charge is neutron? Everett. Negative, correct. Nucleus is inside the middle of the atom. Ohm, some fella who gave us a law. What's Ohm's law? That is Ohm's law. Voltage equal amperage times resistance. Power factor, you don't know about that. What charge is proton? Well, positive. The number of electrons and protons are the same. Chemistry and physics. Okay, let's do some examples. So let's think about that. Let's do some examples now. I'll do fuel, then I'll give you a chance to do fuel. I will check together. Where's my sweater? So if the voltage is 120 volts, resistance is half an ohm. What is the current? Current equals what?
Amps.
Oh. 60. 240.
So it's voltage over resistance, right?
Yeah.
So 120 over 0.5. So 240.
240.
You were wrong.
60.
Wait, no, yeah, it's half of
You're
60.
dividing by half.
Oh.
Yeah. That's why I write things down. Of course, 240 amps is a lot of amps. That's not unrealistic. But again, you get the gist of it. Take it step by step. Don't jump steps. And use the calculator. If the voltage is 220 and the resistance is 0.5, what is the current? So the same thing, same equation. This time I have 220, 0.5. What do I get? Again?
440.
440.
440.
0.5 is 40. 440. If the voltage is 110 and the current is 5, what is the resistance? So resistance equal what? I will go to resistance, cover the resistance, voltage over amperage. So voltage over amperage, 110 over 5. What is that? 20.5 ohm. Close enough. More examples. If the voltage is 120 and the resistance is 0.5 and the current is 240, what is the power? So if I need the power, we'll go to the power law. I need voltage and amperage, right? Do I have the amperage?
Yeah.
Do I have the voltage? Okay, then I can find the power. Just multiply. Now it's 60. 60 watts. Is it? No.
No.
240. What do we get? 28,800 watts. 28,000 watts, which is translate 28.8 kilowatts. Trying to get used to the kilowatt thing because you always don't see kilowatt because it sounds better when you put it down. If the voltage is 220, the resistance is 5, the current is 44, what is the power? So power is voltage times amperage. I have amperage and I have volts. Multiply them together. And I should get 9.68 kilowatt hour. We have some more? We have one more. If the voltage is 110 and the current is 0.868, the resistance is 160, what is the power? Again, power is voltage times amperage. That will give you 74.8 watts. There are a few examples now I'm going to give you so you can work on it by yourself or we can check the answers together. And in this case, you might be required to find the power where you don't have the amperage. You only have the voltage and resistance. So you're going to find the amperage first, then plug it back in. Okay? Yeah, let's try that. Okay.